Assalamu alaikum everyone, welcome to the course of real-time embedded system. Today we are going to start chapter number 4 and this is going to be our lecture number 16, and in this chapter we are going to we will continue our discussion about standard single purpose processor peripherals. In previous slides we talked about timers, counters, watchdog timers, and today we will talk about some more standard single purpose processor. So let's start it. So in this slide we are going to talk about UART. So you might have heard about this UART, and UART is mostly used for serial transmission, and UART stands for Universal Asynchronous Receiver Transmitter. As you can see, this is our sending UART, this is our receiving UART. Data is being sent serially. However, at the source the data is in parallel form, and at the receiver the data is in parallel form. So it takes parallel data and transmits serially, receives serial data and converts to parallel. We use parity bit for error checking. For example, if we have like number of ones even, we make them odd by adding odd parity. So at receiving side we can verify if number of ones are odd, it means that data is received correctly. If the number of ones are changed to even, it means that there is some change or there is an error. So we can have even parity or we can have odd parity. Odd parity means that making the number of ones odd, and even parity means making the number of ones even by adding 1. We have start bit at the start of the data and we have end bit or stop bit at the end of the data. Now, the rates at which bits are sent and received is called baud rate. So baud rate is basically the rate at which bits are sent and received. Baud rate is basically the number of changes in signal per second. Number of changes in signal per second. Whereas bit rate is number of bits that are sent over a connection in 1 second. And bit rate is usually higher than baud rate. Now, configuring baud rate is usually not as simple as it seems. For example, if we want to have a baud rate of 4800, for example, UART of 8051 must use the following equation. We need to use this equation in order to find out the baud rate. So here in this equation, 2 raised power S mod is basically 2-bit special function register. This is oscillator frequency, and then TH1 is 8-bit rate timer register. Okay, so this is 8-bit timer register. So we can also use this UART for voltage converter. Like we can say like this is high and this is low, so kind of a converting voltages. Okay, so final thing is that we can also use general purpose register or general purpose processor to implement UART in software. So we can make UART using software rather than hardware. So that was about the UARTs. You need to remember what is baud rate, what is bit rate, how we can calculate baud rate, what is parity. Let's move on to next slide. So in this slide we are going to discuss about LCD controller, its cores, its control words, and then finally we will talk about a simple LCD code. So let's just start with what is LCD, how it can display images or text. So a liquid crystal display LCD is a low cost, low power device which is capable of displaying text and images. LCDs are extremely common in embedded systems since such systems are not equipped with monitors like desktop computers. LCD can be found in numerous devices like camera, watches, fax machine, photocopy machines, and calculator. The basic principle of one type of LCD. There are so many types of LCDs that are available in market, but one type of LCD known as reflective LCD. It works as first incoming light passes through polarized plate. Next, the polarized light encounters liquid crystal material. If we excite a region of this material, we can cause the material molecule to align, which then causes the polarized light to pass through material. Otherwise, the light does not pass through. Finally, the light that has passed through hit a mirror and reflects back. So the extended region appears light up. So not the extended, the excited region will appear light up. Another type is absorption LCD. Absorption LCD works on the same phenomena. However, it uses black surface instead of mirror. So light reflects back from black surface rather than mirror. So in this first side, you can see that we have a microcontroller. The enable signal is coming from the microcontroller, the read-write signal is coming from the microcontroller, and then this RS signal is coming from the microcontroller, and then these 8-bit data is coming from the microcontroller to LCD IC, which is interfaced with LCD screen. So these are the code. These code will be used in this control word. For example, if you want to clear all display and return cursor to home, this is the data that we need to set. In RS we need to set 0. In RW, which is read write, we need to set 0. In all the data bits we need to set 0. However, DB0 we are setting 1. So once you set DB0 to be 1, clear all display and return cursor to home. So for example, if you want to move cursor and shift display, we need to set DB4 to 1 and DB3 to S/C. So we can see here S/C, if 1, display shift, 0, cursor movement. So you can set it 0 or 1. So if however we want to move the cursor, so we have to set it 0. Okay. So in DB2 R/L, what does it represent? R/ is 1, shift to right. If it is 0, it will shift to left. So it depends where you want to shift. If you want to shift to left, you can set left or right. And these are like don't care, so you can put any value, doesn't matter. So finally, like set interface data length, number of display line and character font. So this is control signal. So RS need to be 0, RW needs to be 0, DB7, DB6 needs to be 0, DB5 needs to be 1, and DB4 needs to be DL. Now what value of DL we can set? 1 or 0. So if I set DL to be 1, it means that I have 8-bit data interface. Okay. Now DB3 N. So if N is equal to 1, it means that we can have 2 rows on LCD. If N is equal to 0, it means that we can have only 1 row. So DB2F, and F means that we can have, if F is equal to 1, it means that we will have resolution of 5 into 10 dots. If F is 0, it means that we will have resolution of 5 into 7 dots. So finally, if you want to write something, we must need to have RS signal 1 and read write to 0, and then finally we can send any data that we want to write. So here you can see in this example, this is the code indicate. So this is our void, this is our function write character. So character is coming in, we set RS to 1, and data bus, wherever the data is coming in the C will be written on data bus, that is DB0 to DB7. So send data on LCD, and every time we write, read, or we set the control word, we need to enable this enable pin. So this enable pin must need to be toggled. Okay. So every time data is sent, whether control word or data, the enable bit must be toggled. So we need to toggle the enable bit. So here you can see that we have function enable LCD 45. So the enable LCD function toggles enable bit as well as it acts as a delay. So here we are enabling and toggling the enable bit, and also we are using delay of 45. So that was about the LCD. So we can initialize our LCD by using these control words, and once it is like initialized, we can write data, and for anything to be done we must need to toggle the enable bit. So that was about the LCD controller, its control words, codes, and finally a simple code for writing something on the LCD. So let's move to next slide. So in this slide we are going to talk about keypad controller. A keypad controller consists of set of buttons. As you can see here, we have set of buttons that may be pressed to provide input to an embedded system. Again, keypads are extremely common in embedded system since such system may lack the keyboard that comes standard with desktop computer. A simple keypad has buttons arranged in n columns, so these are n columns, by m rows, so these are m rows. These are column 1 2 3 4 and 1 2 3 4 rows. The device has n outputs, each output corresponds to a column, and other m outputs, each corresponding to a row. When we press a button, one column output and row output go high, uniquely identifying the button pressed. For example, if we press this button, we are going to M1 will be high and N3 will be high, uniquely identifying the button press. To read such a keypad from software, we must scan the column and rows. So we must scan these columns and rows. The scanning may be performed by keypad controller. So keypad controller perform this scanning. Actually, such a device decodes. So what we do here, we decode rather than the control. Stores the code corresponding to the button. So this button has some code which will be stored in a regular register. So this is the register where the code is stored, and sets output key high. So once we press the button, this will become high and we will have a key code here. Our software may poll this after every 100 milliseconds rather than checking the keypad pin that whether it is high or not and then checking the code. What our processor can do, that it can poll after software can do, it can poll after 100 milliseconds. So after 100 milliseconds it can check whether the key is pressed and what's the code and read the register, that is key code, when the K pressed pin is high. Or output can generate interrupt, or we can generate interrupt eliminating the need of polling. So this key press can generate the interrupt, and at that time we can read the key code register. So this is our N cross M keypad controller, which is used in many embedded systems because we do not have the presence of standard keyboard. Okay, so it acts like a decoder rather than a controller. So that was about the keypad. Let's move on to next slide. So in this slide we are going to discuss pulse width modulator. So pulse width modulator generate pulses with specific high and low times. Okay, so these are three different graphs. As you can see here, we have a clock signal and pulse width modulator output. So in this particular graph, in the number 1, you can see that if we have a maximum voltage of 5 and our duty cycle is 25, it means that we are going to turn on the signal for 25% of the time it is going to be high, and 75% of the time it is going to be low. So if we multiply 5 with 0.25, we are going to get 1.25. So the average voltage of the PWM is going to be 1.25. Similarly, you can see here that half of the time our signal is high. It means that duty cycle is 50 and half of the time it's low. So our duty cycle is 50. So 50 duty cycles and we have a maximum voltage of 5. So 0.5 into 5, it's going to be 2.5. It means that our average pulse width modulation voltage is going to be 2.5. Likewise, here you can see that our duty cycle is 75. 75% of the time our signal is high and 25% of the time our signal is low. So 0.75 into maximum voltage of 5, we're going to get 3.75 volts. So it means that pulse width modulator will have an average voltage of 3.75. So duty cycle is the percentage time high. Scale wave has 50% duty cycle by default. 50% of the time it is on and 50% of the time it's off. Now, the common use of pulse width modulator are control average voltage to electric devices. So we can increase the average voltage and we can decrease the average voltage by using pulse width modulator, which we can also do with DC to DC converter. Like DC to DC converter is used as a buck in which we decrease the voltage, and in boost mode we can increase the voltage. Or in digital to analog converters, DC to DC, we can also use it in DC motor, speed controlling. We can use it in dimmers. We have seen that in dimmers we either increase the voltage or decrease the voltage. In lights, we can increase the voltage of the light or decrease the voltage of the light. Another use of these pulse width modulator is to encode commands. Encode commands, for example, we have a remote control car and we are sending in a pulse width modulator signal which contains like the car needs to turn left, the car needs to turn right, or it needs to increase the speed. So receiver uses the timer to decode. So we send encoded commands and receiver uses timer to decode. So this is the function of the pulse width modulator, either to increase or decrease the voltage, and that is average voltage. So now let's have a look at the example in next slide. So in this slide we are going to talk about controlling a DC motor with pulse width modulator. So in this diagram, the top one, you can see that we have a circuit of the pulse width modulator which comprises of clock division, which you already knows that we can divide the clock in order to slow down the clock increments, and this clock div determines the period of the clock, and this is a counter from 0 to 54. This is 8-bit comparator, and this cycle high is 8-bit register, and this clock div is also 8-bit register. And this cycle highs basically determines the duty cycle, whereas this cycle clock div determines the period of the clock. So how we can find out what is the period of the clock? We can try different values of clock div and we can check the speed of the motor. Likewise, for cycle high, if we have cycle high to be 255, and if we convert 255 to hexa, it will become 5FF. Okay, so if cycle high is FF and we see that we have 0 to 254, which is 255, so we are going to have PWM output to be 1. Why? Because as long as counter is less than cycle high, so as long as this counter is less than this cycle high, we are going to have 1. So if this is 255 and this is always less, so we are going to have 1. So 255 in cycle high means that we have 100% duty cycle. And if we have 00 here, it means that we are going to have 0% duty cycle. So as long as counter high is less than this value, we are going to get 1. If counter become greater than cycle high, we are going to get PWM 0. Okay, so what happens here, we give a clock here, we divide that clock, we slow down the clock, and then on the basis of this clock, this counter increments. So it will become 0, we compare this with cycle high, then this will become 1, we compare this with cycle high. As long as counter value is less than the cycle high, we are going to get 1 here. So this is how the internal structure of pulse width modulation works. So here we have input voltages 0, 2.5, 3.75 and 5, and here we have duty cycle, that is percentage of maximum voltage applied. So if we have a 0, it means that the speed of the DC motor will be 0, it means 0 duty cycle. If we have 50% duty cycle, it means that we are going to have half voltage. Half voltage means 2.5. So the half of 5 is 2.5. It means the speed of the motor will be 1840. And if we have input voltage of 3.75, we are going to have 75% of the duty cycle, and the RPM is going to be 6900. Likewise, if we have input voltage 5, it means we need to have 100% of the duty cycle. So that was about the relationship between applied voltage and speed of the DC motor. So now you can see here that PWM alone cannot drive the DC motor. So here what we have a MOSFET here, and this MOSFET is going to drive the DC motor. So the signal will come from processor, it will apply at the gear of the MOSFET, and then this gate will, and what we are going to apply at the gate, these will be the pulses of the pulse width modulator, and then the DC motor will be driven. So for a motor to run at 4600 RPM, for example, we want this motor to run at 4600 RPM, we need a duty cycle of 50. So for a motor to run at 4600, we need a duty cycle of 50. To compute the value needed in cycle high is 50%. So if we need 50% here, how we can compute? We can multiply 254 with 0.50, which returns to be 127, and 127 hexa is 0 into 7F. Okay, so we need to put that 7F here in cycle high, and we need to put FF here. Why we need to put FF here? Because we have checked that in case of FF, we have the best working of the circuit. So we can apply different values for clock diff, and on the basis of DC motor speed and its continuity, we can set the value of clock diff. So if we want to have 4600 RPM, what we have to do? We have to put PWMP, that is the period, is equal to 0 into FF, clock diff, and now for duty cycle, PWM1 is equal to 0 into 7F. So, and this while will continue as long as we don't have anything. So the motor will run at 4600 RPM. Let's pose another example. For example, if we want motor to run at 6900 RPM, we need 75% of the duty cycle. So in that case, we will multiply 254 with 0.75, which will become 191. And the hexa of 191 is 3B, sorry, BF. So 191 hexa is BF. So we are going to put BF here. Okay. So in that case, our motor will run at 7500 RPM. So here there is a mistake. It is not 1840 for 50% of the duty cycle. This speed is going to be 4600. So that's why I have told you that for 4600 we need to set duty cycle of how much? 50%. And we cannot just connect DC motor to pulse width modulator because PWM does not provide enough current to run the DC motor. To remedy this problem, we use a NPN transistor to drive DC motor. The code and schematic used for example are shown here. So you can see here. So that was about DC motor control. Why we use this? Because in order to increase the current. So as I've told you in previous slide that for driving most motors we usually use MOSFET in order to increase the current. So here we are going to discuss why we use driving motors. So high current devices like motor, relays, solenoid, buzzers and light bulbs can require more than 5 milliampere of current, even though voltage level may be same. So for example, if there is a bulb that requires 5 volt, which we can generate from our general purpose processor input output, but requirement goes beyond 500 milliampere, it means that we need some sort of driving motor IC. So even though voltage levels may be same, digital output from general purpose processor input-output parallel port typically drive only 5 to 20 milliampere of current. So the current that you get from the port of input-output port of general processor is up to 20 milliampere. They cannot drive high current devices directly, and trying to do so will blow out the output circuit. So we need to have driving motor ICs. Now, what does driver circuit means? A higher current driver circuit must be added after the digital output pin and before the device. So we need to have a driver circuit before the device to which we are driving or after the output from where we are generating the digital output. A driver circuit typically uses a discrete power transistor. So whenever you are going to look at the driver circuits, it will comprise of power transistor. For DC motors, consider using H-bridge circuit module. So most of the time when we are going to control DC motor, there is one common IC, that is H-bridge. So we are going to look at the H-bridge circuit module. It contains 4 power transistors that can also reverse the motor. So the advantage of using H-bridge is that we can drive the motor in forward direction as well as in reverse direction. Diodes are often used for additional protection. So we use diodes for additional protection across the load on motors and relays. When you turn off the current in an inductive load, it generates a reverse voltage spike that might damage the transistor, which is back EMF. So the diode shorts it out. So we use diode in order to protect our circuit. Okay. So this is the circuit of basic H-bridge with 4 power transistors that provide current for the motor. In this circuit, you can think of the power transistor functioning as on-off switch. So these are the on-off switches 1, 2, 3 and 4. 2 digital logic level inputs. So these are forward input and this is reverse input. Turn the transistor on and off. So these input turn the transistor on and off. In the center circle M, this center circle M stands for motor. This is the DC motor device being driven. So these are the control of the H-bridge function. So once we have input 1, 0, it will run in forward direction. DC motor run in forward direction. If we have the input 0, 1, it will run in reverse direction. If we have 0, 0, it will stop. And if we have 1, 1, it will break. And motor terminal shorted or power supply shorted. Okay. So the break function requires a more complex decoder circuit to control the power transistor. Check the H-bridge datasheet to make sure it is ported before using it. In simple H-bridge circuit, the 4th state must be avoided. Otherwise, it will short the power supply or motor terminals. So we must need to check the datasheet whether this 4th operation is ported or not. In simple H-bridge circuits, we cannot use this 4th option, otherwise your power supply will be shorted or the terminal will be shorted. So let's move on to next slide. So here you can see that we have applied the input 1 and 0 here. So forward input is high and reverse input is low. So the voltage, so this is the path. You can see the current will flow like this and we have forward motion. In the second, in forward we are applying low and in reverse input we are applying high, so the current will flow in opposite direction. So we'll have reverse direction of the motor. So in this slide you can see the figure of the Fairchild Fan 8100M low voltage H-bridge DC motor driver IC with 1.5 amps transistor. So this IC can drive 2 DC motor of 1.5 amps each. So if we combine the output of these two amplifiers, we can drive a 3 amps of DC motor. And one thing more about this, that you can see here we are this power ICs are equipped with diodes. So these diodes are used to prevent the um, break function. So it provides break function and it prevents the power supply shortage. Okay, so here we can use the function of 1 and because we are provided here with diodes, and it will not cause any harm to your circuit or terminals. Okay, so your power supply won't be shorted out. By pulsing the drive circuit on and off, so we can turn this circuit on and off at several kilohertz. The speed of the motor can be controlled. So how we can control the speed of the motor? The speed is proportional to pulse width. As I've just told you in previous slide that once we are going to increase the duty cycle, the voltage will increase and the speed will increase. So most of the time we use feedback mechanism. Feedback is needed to achieve the accurate speed control since speed varies with motor temperature and voltage. So most of this time what we do, we connect a optical shaft angle encoder in order to measure the speed of the motor shaft, and then we use the signal for feedback purposes. Okay, so this was just about the IC, how we can use this IC, what's the purpose of dual edge bridge DC motor driver IC, and it is widely used in toys. So this is the higher current edge bridge module, typically uses discrete power transistor assembled on board. This dual edge bridge module switches up to 10 amps at 24 volts. So you can use 10 amps as this 24 volts. The 8 power transistor can be seen arranged on the right side of the board. So these are 8 power transistor, 1, 2, 3, 4, 5, 6, 7, 8 on the right of the board. So this is how your edge bridge, dual edge bridge look like, and it is being, the picture is provided by robotics connection. As you can see here, robotics connection, 10 amps dual edge bridge. Okay, and these here you can see that motor 1, motor 2, and these are 12 volts and ground. So in this slide we are going to talk about analog input and output. So for analog input, convert to digital using analog to digital converter, A to D or ADC, whereas analog output, convert digital output to analog using digital to analog converter. Design issue that we need to consider are number of bits for accuracy, conversion time delay, sample rate needed by the application. So these are the design issues that we need to consider while designing the analog to digital converter or digital to analog converter. So let's move on to next slide. So all these devices require a time delay when performing a conversion operation and are accurate to a specified number of bits. Typically the conversion time are in microseconds range and accuracy is in the range of 8 to 20 bits. So we measure the accuracy in terms of bit. In general, faster devices are more expensive devices. With more bits of accuracy, more cost come. So in this slide we are going to talk about analog to digital converter and digital to analog converters. So first look at this table. So in this table we are using 4 bits because we want to represent 7.5 volts from 0 to 7.5 volts. So if you see here that we have a resolution of 0.5 volts. Why we have a resolution of 0.5 volts? Because our maximum voltage is 7.5, our minimum voltage is 0 volts, and this is difference of 0.5 volts between every 2 consecutive levels. So you can use this formula. Resolution is equal to Vmax. So Vmax is 7.5 divided by 2 raised power 4, that is 4 bits, minus 1. So if you divide 7.5 divided by 15, it is going to be 0.5. So our resolution is 0.5. Here we are mapping input voltage, that is in analog to digital output. So for example, in the case of, for example, here we have 3 volts. So here you can see that 3 volts. So our analog voltage is 3. E represent here analog voltage, and our maximum voltage according to this table is 7.5. So 3 divided by 7.5 is equal to D. So D is our desired digital signal divided by 2 raised power 4 minus 1, which comes to be 0110. So what is going to become 1, 2, 4? So it is going to be 6. So D is equal to 6. If we convert 6 to binary, it will become 0110. So it is the opposite. Here we have the analog output. So for example, if we have analog output, that is, so we are mapping from digital inputs. So digital input is 0110 and the analog output is coming to be 3 volts. So 0110, just put D to be 6 and 4, V max 7.5, you are going to get analog voltage of 3. So this is how you can map analog to digital and digital to analog. So keep in mind this formula. Now you can see that this is very iterative process. Like what you need to do, you need to form this table, and then we need some sort of timer or a counter to keep track of these consecutive voltages. So in order to overcome this problem, most of the time we use successive approximation converters, which we are going to look in next slide. So this is the block diagram of successive approximation analog to digital converter. Here we have a clock, we have successive approximation register, and this is end of conversion signal, and these are data bits which are going to digital to analog converter, and digital to analog converter has a V reference, and V reference is basically our reference signal, and V input is the input signal. Then we have sample to hold. We are going to compare two values here. Okay, on the basis of these values, if the value becomes greater, we are going to put 0 here in the SAR, successive approximation register, on the data bit. I'm going to explain this whole circuit with the help of an example in next slide, so hopefully things will become more clear. So here we want to do analog to digital converter. So we have an example. Given an analog input signal whose voltage should range from 0 to 15 volts. So the range is from 0 to 15 volts. So V min is 0 and V max is 15 volts, and an 8-bit digital encoding. So we have 8 bits. Calculate the correct encoding for 5 volts. So we have analog 5 volts and we need to check what is the digital equivalent. Then trace the successive approximation approach to find out the correct encoding. So if we use direct method, that is 5 divided by 15, which is our analog voltage, divided by, that is your Vmax, so Vmax is 15, is equal to digital divided by 2 raised power 8 minus 1, which comes to be 85, and the 85 binary encoding is this. So in successive approximation, we start from the middle. So choose a common point. So how we can start from the middle? Vmax plus Vmin. So Vmax is 15, Vmin is 0. So we are in the middle. Okay. So 1 by 2, it becomes 7.5. So you can see that 7.5 is greater than our encoding, that is 5. So what we are going to do? We're going to put 0 at the first place in the most significant bit, and then we are going to use 7.5 and 0, which becomes, and after dividing by 1 by 2, it becomes 3.5. No, now we can check that 3.75 is less than 5. So we are going to put 1 in this successive approximation register, and next what we are going to do, we're going to replace 0 with 3.5. Okay. So 7.5 plus 3.5 divided by 2, it becomes 5.63. So 5.63 is greater than 5. So what we are going to put, we are going to place 0, and we are not going to replace 3.75. Instead, we will replace the 7.5 with 5.63. So what we are doing here, we are replacing the minimum and maximum voltages here. So in next, you can see that we have 5.63 plus 3.75, and the voltage comes out to be, after dividing by 2, it comes out to be 4.69. So 4.69 is less than 5, so we are going to replace the minimum 3.75 with 4.69 and the maximum limit as it is, and we are going to put 1 here. So here 5.16, so again 5.16 is greater, so we are going to put 0, and we are going to replace maximum 5.16 and 4. And once you reach the last one, you can see that we have encoding scheme which almost equal to 5 volts, and the encoding scheme is 01010101. So here 01010101. So this is how our successive approximation analog to digital converter works. Now you need to tell me in next lecture why we are using this successive approximation approach in order to find out the correct encoding for some analog signal. What is the significance? So that was for today's lecture. We will move on to next chapter in our next lecture. Thank you very much.